This project is related to MATLAB based implementation of finite volume LWR traffic flow simulation with dynamic visualization. LWR is basically Lighthill Whitham Richards. Basically, he was a scientist which proposed a microscopic traffic flow model using the monotonic upstream centered scheme for the conversation laws. We call it MUSCL, short form MUSCL, and coupled with the Horton Laxman-Lear flux method basically. And Horton Laxman-Lear means HLL flux method. So this method introduced by Lighthill and Whitham and Lighthill both were the scientists and who proposed the vehicular movement using the kinematic wave theory. So the finite volume approach basically is the mass conversion and shock capturing accuracy in density evaluation. In the MATLAB, we have just improved the efficiency, implementation, visualization, real-time animation of traffic density propagation, and various using the various initial conditions such as bottleneck, Gaussian, and two-state profiles are analyzed. Okay. So Richard basically later refined this platform, this framework, introducing a conversion-based representation of traffic density and flow. So this is the abstract of article and the keywords with the introduction of traffic flow diagram, traffic modeling, how we can use LWR formalization using the stable microscopic behavior, and then how we can use the behavior of vehicles to simulate the congestion bottlenecks and shock waves propagation. So here is the characteristics of solution of LWR, which provide us the complete flow chart of traffic according to the specific time basically. Okay. Despite its like we called it simplicity solving the LWR model accurately, we need to require a robust numerical schemes capable of handling discontinuities without generating spurious oscillations, basically spurious oscillations. High resolution, basically finite volume methods, particularly those incorporating the monotonic upstream centered scheme for the conversion laws basically, and the Horton-Laxman-Lear flux. So they basically demonstrated the excellent performance for the hyperbolic systems, and these schemes basically stabilize and provide us the stabilize and precise results even under deep traffic gradients. Okay. So here is like a LWR model for the series of traffic lights, and then background is here which I have defined accordingly. So yes. And yes, background is here, literature review and research motivation. This is the same like which I have explained to you in details. So the thing is that next one is the objective. Objective in which we need to formulate. Basically, we need to simulate the model which will provide the finite volume solver and stable and accurate finite volume solver for the nonlinear traffic conversion equation. And next we need to implement MUSCL, slope limiter, and HLL flux basically. And here is a problem statement with the mathematical model. Mathematical model basically provide us the numerical configuration with the boundary setup. And these are the numerical, this table represents the numerical scheme with flux function, reconstruction, boundary condition, and initial conditions according to the its configuration. And these are the equations used in our model, and these equations basically depend on the local traffic density through an empirical and theoretical relations known as fundamental diagram. So in this article, basically, we have just added the green shield model, which is adopted, which defines the relationship between velocity and density as well. So here is the equation of velocity and density according to the traffic lights green shield model. Okay. So it also we have just explained like what Vmax is and what rho max is. Basically maximum traffic density, which is jam density, and Vmax is a free flow speed as well. So again, the wave propagation speed versus and the equations of LWR model, free flow body as well. Okay. So everything is added in here perfectly. So um, it means that that needs to be added accurately. Okay. Correct. Fred Richards Levy as well, conditions as well. So here is the methodology. Methodology is basically research integrates analytical modeling, numerical discretization, and MATLAB simulations of all the Lighthill, Whitham, Richards as well. In the table, next table is basically parameter model of parameters and the notations basically. These are the parameters used in our MATLAB simulation and for the purpose of analysis and the MATLAB simulation. And this table represents the performance and error matrix basically. Okay. So here is the MATLAB results, which is the live animation of density fundamental diagram of space and space-time density as well. Okay. And next one is initial versus final density flow diagram. Third one is fundamental diagram of fundamental traffic flow diagram basically, in which we have implemented the green shields model according to the rho and the traffic flow velocity speed. Space-time density, there is a graph of space-time density, and next is snapshot of everything. Okay, density of snapshot selected time instances. Then conversion of mass as well as the mean speed evaluation. Okay. Next is flux at domain midpoint, and next one is L2 evaluation according to the error evaluation of density field. Histogram of final flux, and then its discussion, results discussion, like how we have used green shields models, space-time plots, confirms with the traffic disturbance, and propagate with physically realistic speeds as well. Now here is a conclusion, and references are added. Let me just provide you the MATLAB demonstration. Here is the MATLAB code. You just need to open and you just need to run it, and you will get the output results accordingly. Okay. See, this is a live animation of traffic flow diagram according to different time with different speed. Time frame is different. We can change accordingly, but it's the output results of final values generated at the 200 seconds. Okay. All the output results are here. You just need to check it and you will get the output results. Okay. So thank you. If you need to ask anything, you just ask me. I will answer your questions. Thank you.